Okay, guys, welcome. As I told you, I will upload a video about summarizing the findings or review of the experiment we did. Okay, let me start with the pipe friction experiment. So, pipe friction, what you did, you measured the pressure drop across the length of pipe. Okay, delta H. Okay, delta H experimental, and then you calculated using the correlation, right? And what you did, you plotted delta P versus Q. In your case, it was all turbulent region, so this was the trend line, and you are supposed to fit a power trend line that gives you delta P proportional to Q power something 1.9 or 2.1 or 2.2. So it is like approximately Q square. So in turbulent region, what we have pressure drop proportional to Q square. It's not linear. So what does it mean? It means that if you double the flow rate, delta P is proportional to Q square. So if you double the flow rate, delta P by delta P1 becomes Q2 over Q1. So Q2 or Q1 is 2, it means it becomes 4 times. Okay. In laminar region, okay, we didn't study in experiment, but by simulation or by theory we can know that in laminar delta P and Q, they are, of course, with increase in flow rate, delta P, pressure drop due to friction in a pipe will increase, but it increases linearly. What does it mean? Linearly means, of course, with no flow there is no pressure drop, right? So it should be like this. So delta P proportional to Q. So this is true in laminar flow. So in laminar flow, it means you are doubling the flow rate, your pressure drop or pressure loss will be doubled. Okay, so this is laminar and turbulent. With respect to the diameter, if we study with respect to diameter, what will happen? In turbulent, in laminar flow, pressure drop, pressure loss due to friction is inversely proportional to diameter. So it's not 1, it is d power 4. This is true in laminar. Okay. When this is true, when we keep the flow rate constant. For same flow rate, if you keep if you measure the pressure drop, pressure loss across different diameter pipe, you will get this relation. So if you plot delta P versus uh, diameter of the pipe, you got something like this. So slight increase in diameter will decrease the pressure loss. Why? For the same flow rate, if Q is same, diameter is more, it means the velocity is less. Velocity is less, it means the pressure drop will be less because the friction will be less now. So this is about dependence of pressure loss in pipe with diameter. This is laminar, and in turbulent we expect something similar, not exactly power 4, it could be 3.75, 3.9. In turbulent region, we depend mainly on experiment. So you have the experimental data, you can regress and get the correlation. So this was about pipe friction experiment, straightforward. Okay, let's come to the flow meter, Venturi meter and orifice meter. Venturi meter, what you did, you calculated the flow rate uh, using this equation, right? Q is CD 2 delta P divided by 1 minus beta. Beta is d2 over d1, right? A small diameter to big diameter. So idea is how they got the discharge coefficient CD. What is CD? C is the correction factor for friction in pipe, friction in Venturi. The losses because of pressure drop, pressure losses because of friction. So delta P measured in lab includes the friction as well. So that's why this is delta P, okay, based on frictionless flow. So if there is frictionless flow, your delta P is this. So this is the pressure drop due to change in area only, assuming there is no friction. But in real scenario, you always have friction. That's why you need a correction factor CD has to be less than 1. Okay, any meter, Venturi meter or orifice meter which will have less friction means high CD. So in turbulent region, CD for Venturi meter is 0.98, right? An orifice has high losses because sudden change in area. Orifice is this, right? So if flow takes place like this, there is flow separation, there is AD. So if we measure the pressure P1 and P2, pressure drop from 1 to 2 point because of the losses, because of the friction is high. Okay, so that's why CD has to be less. Why? To get rid of the pressure drop coming because of the losses, because of the friction. Okay, okay, 1 minute, let me go back. And if you use the Bernoulli, assuming frictionless flow, you get this one, 2 P1 minus P2 divided by rho, and this is all square root. Okay, this now P1 minus P2 is assuming there is no friction. Okay, now in real you cannot measure the frictionless flow or pressure drop due to without friction. So in real you always will have pressure drop with friction and because of change in area. So this P1 P2 always will be more. So that's why you include the CD term here, so that CD will be less than 1, and then it takes care of friction pressure drop due to friction. In Venturi, we know that this design is such that so there is not much loss due to friction. Okay, this angle is smaller. So from here to here, streamline flow from 1 to 2. So the pressure drop coming because of the friction is very less. That's why CD is almost close to 1 in orifice. Sorry, in Venturi. In orifice is 0.6 because we have more friction. Okay, so hope you understand this CD. Now you have calculated the CD. How? By calculating this term, this term, which you can say Q ideal, and you have you know the Q actual, Q measured by rotometer. So this, you divide this term by this term, you get the CD, right? Then CD you have plotted versus Reynolds number. Okay, at high Reynolds number, as we know that this is one value, isn't it? So for Venturi meter, it should be like here. So this is around 0.98. But at a smaller Reynolds number, close to laminar, this is like this. So initially it is okay, like this. So start with at low Reynolds number is small, at high number is increasing and become almost constant. Now, how to explain this? This is CD, okay? CD. How to explain this? So CD is less. It means we have friction, we have losses. So at low Reynolds number, what is happening here? This is interesting. Usually at high Reynolds number, we have more losses. But the Venturi is designed such that at high flow rate, the streamline flow will be better. The flow will stick to the wall. But if flow is slow, then maybe we have flow separation, and it may be some eddies and losses. So in laminar flow, we have more losses in venturimeter. That's why your CD is low in this range, and then it becomes constant. Okay. We can also find CD. Okay. What we did, we measured Q and delta P, isn't it? This is Q real versus delta P. So Q, and we if we plot Q versus delta P power half, okay, then that should give you a straight line. Okay, and slope is all slope will be all of this root 2 over root rho times 1 over minus beta power 4. This is slope. And with CD, with CD, this is slope. If we plot flow rate versus delta P power half, and then from slope value you can get the CD. Okay. What else? Then we also measure the H3. So H3 was the recovered pressure after area is going back. So recovery pressure percentage recovery is high in Venturi meter. Okay, low in orifice meter. Why? Because Venturi is designed such that area is once area is decreased, now slowly you will find as the diverging section is smaller. So diverging section is bigger than converging section. So slowly it recovers. Area increases slowly, velocity is decreasing slowly. So it is pressure is recovered. So P3, P1, this is P2 here. P3 is almost close to P1, or not much less than. So recovery of P3 over P1 is the recovery pressure. Percentage recovery is high in Venturi, low in orifice. Why? Because this is orifice. Sudden change in area, it goes like this. Then flow, there is a lot of eddies there. So 1, 2, 3. Even after area is increased, is back to normal, as in 1, your P3 is less. Why? This is lost forever in terms of heat, in terms of friction, and so on. So that's one of the disadvantage of orifice meter. Okay, I think that's it. I'll make it short. Thank you.